Okay, I'm about to embark on my evening learning sessions, and essentially, the idea behind this is I want to take on the process of learning how to, build low level technologies from scratch, right? And I haven't spent most of my career working around things like that, but I've been using a lot of TypeScript and JavaScript recently. I wanted to shift to Go, but I wasn't fascinated by it enough. And yeah, I judged things especially by my fascination. Um, I wish there were better metrics. They probably are, but that's how I tend to judge these things. So I decided to go with Rust, and I've been finding Rust interesting. So I have a project I want to work on. I don't know how long it will take me, and I'm pretty much going to build through the entire process. Possibly, yeah, right. This is just a means to keep myself accountable. And I have this sort of 2 hours sessions which I want to have somewhat daily. So I want to actually like take this one as part of my process in general. And then from there work on side projects or yeah, side projects, mostly video projects around other things that I do and work on. But yeah, let's see about these notes. Okay. Um, let's see. This might be one of my first few times using OBS, so I might be messy with it soon. But I'll do my best. I'll do my best. Possibly my streams get better with time, but I'll do my best. Let's see. Okay. Okay. Not window application capture. Let's see. Window capture. Obsidian. Thank you. Okay. I think I should be getting the hang of this. Sorry, this was pretty much taking up my entire space. I should adjust this equivalently. Yes. Good. So I can have this somewhat like this. Do this like this. Okay. This will work. This won't work. Yeah, I'm getting used to it too. Okay, so this is what I want to work on, and let's see. Let's get my editor in here. Okay. There we go, there we go, there we go. Okay. Let's transition that. Okay. So as you can see, I'm currently transition. Okay. 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 So I think I've got what I'm looking for. So I have this to work to, right? Building a Rust database, and that's building a database using Rust. And I don't know the first thing or the second or the third about building databases. Hold on, I need to make sure this actually aligns properly. Give me a second. Yeah. So as I was saying, I don't know the first thing about building databases, right? And let me go to my project sets, essentially. Yeah, I have a couple of Rust projects here. Just mostly touching on some manual stuff. Getting really familiar with the language. I actually understand a large portion of it. But you see, I want to fight the borrow checker, and I want to fight it properly. So, with that said, we're going to go ahead and start a new Teamworks session. Well, I have this Teamworks thing recording my entire the state of my entire workspace in general. So let's see, let's create an open source project. Open source because eventually it will be open. I might start it as a private project. I hope to take this to some really good levels and learn a lot with respect to databases, right? As you can see, I have a bunch of open source projects that I'm actually looking closely at, and I would have loved to well, most of them are in Rust, Yazi, Z, and Electrium Rust, and I would love to contribute to those. But open source these days feels like as if you're fighting the benevolent dictator, something like that, right? So you're struggling most of the time to get things out there, and I want to really learn a lot very quickly. So let's see about making a new project, right? So let's see, cargo, not one, is it new? Yeah, yes, cargo new. Let's call it, I want to give it an interesting name so that I will be able to possibly actually use this database in some operations, personal operations. Who knows? It might just be a revenging of SQLite, depending. But I don't have the knowledge yet, so I'm gonna have to acquire a lot of this knowledge. 2 hours to go, so let's pick up the pace, shall we? So let's see. Cargo new. What do I want to call this? Well, first word that came to my mind. Okay, let's do this. Okay. At least some. I don't know about this. So let's see. Come on. Get out of the way. Okay, we don't have a main. Well, I don't know if we need the main. Well, it will need the main because the database should be initializable, right? But how would this work? Well, thankfully, I have a good amount of resource here in this node. So the first part talks here about building a database like Postgres, right? In Rust. Yeah. Building a database like Postgres in Rust is an ambitious and rewarding project. Yep. That will deepen your understanding of databases generally, and below is a high-level technical architecture generally, right? A high-level architecture of a database system like Postgres, broken into key components. Now, the core components of database systems in general are the storage engine, right? I know that they do store things in files, right? But what's the structure of the files, right? So, the storage engine is responsible for managing how data is stored and retrieved from disk. It includes the data store, the heap files, right, within it, the pages. Now, heap files are stored rows, tuples on ordered heap files, right? Interesting. The rows are tuples, okay? And the pages are divided into fixed size page, right? That is 8 kilobytes size, depending. Yeah, I think it's fixed. And they are units of IO operations essentially. Now, free space map, it tracks fixed spaces within pages for efficient storage allocation. Interesting. So we'll be doing some tracking of storage within files themselves, right? So more like reading both files and checking for like open spacing and stuff like that. Who knows? Indexing, right? B3 is commonly used for indexing, e.g., primary keys and unique constraints, right? Then hash indexes for fast equality lookups. Then gist/gin index. What's that? For advanced indexing, e.g., full text search and geometric data. Okay. We have a look ahead logging system, ensures durability by logging changes before they are applied to the database. Okay, and used for crash recovery and replication. Ensures durability by logging changes before they are applied to the database. Oh yeah, like a change log, so that you can actually be able to use it to recreate the. So you're able to use it to recreate the, what do we call it? To recreate the queries that go in. Now, query processor. I have to brush up on my SQLs, right? Because this is going to be an SQL database, purely relational database. Later, I can think about building around non-relational databases. But let's see, query processor. Now the query processor passes, optimizes, and executes SQL queries, right? So which means there's a bit of a compiler type thing going on here, because I'm going to be passing a query language. This is going to be fun. I haven't done the compiler course yet. I have, and surprisingly, I didn't finish it when I was in school. Well, I will do it again. I actually understand the basics, but yeah, I have to brush up generally. So I have to write a parser, converts SQL text to abstract syntax tree. Then the planner/optimizer generates and executes generates an execution plan by evaluating different strategies, right? E.g., the join order and the index usage. Then uses cost-based optimization to choose the most efficient plan. And then the executor executes the query plan by interacting with the storage engine, implements operations like scan, join, sort, and aggregations, right? Now, transaction manager, it manages this is about managing the transactional nature of database updates, right? Being that they should be atomic, and that is, they should be reversible, right? If one of the operations fail, every operation in that particular transaction flow should also be rolled back, right? So the atomic nature of that operation. So essentially, it ensures ACID, atomic, consistent, isolation, durability properties, right? And so this involves concurrency controls, multi-version concurrency control, allow multiple transactions to read and write concurrently without blocking. Interesting. Yes. Okay, I'll love that. And obviously there'll be a lot of async rust in this. Yeah, a chance to actually fight. So let's see, locking manages locks for resources, rules, tables to prevent conflicts, isolation levels, implement levels like read committed, repeatable read, and serializable. Okay, recovery, use the look ahead, the right look ahead to recover from crashes and ensure durability. Client communication, that's implement a wire protocol, okay, for a client to communicate with the database server, pretty much, since it's a server, which means we need a main. We're going to be running some connection points. So connection pooling, managing a pool of connections to handle multiple clients efficiently. I would love this. Then the next is about utilities, additional components that support the core functionalities. That is vacuuming, that's deleting dead tuples and reclaiming spaces within the system, the files themselves, right? Backup slash restoration, providing tools for backing up and restoring the database. Replication supports as synchronous or asynchronous replication for high availability. Okay, so we have an architecture diagram here. Now, here's a simplified architecture diagram for a database system. Give me a second. Let me just check if I'm still on stream. Yeah, I am. Okay. High level architecture diagram. Here's a simplified architecture diagram for a database system, client application, query processor. Okay, so the client connects to the query processor, which we connect and essentially run through the planner and executor to interact with the utilities and the storage engine. Okay, the storage engine is essentially managing the heaps of files, and the heap files generally the indexes and the WAL. Let me just make sure I have that full word, my write ahead login. Yes, yeah. So login before write, pretty much, so I can always rewrite. So write ahead login, and then the client communication protocol and connection pooling. So that the write ahead logger connects with the client communication protocol and pooling generally. And we have the transaction manager and the locks generally for the management of each transaction entry to make sure it is atomic in operation. We JavaScript people, sometimes we miss the meaning of the word atomic in programming. Let me just look at that again. Yeah, an operation that happens at once without stopping in the middle. So essentially, there's no an atomic operation has no what's the word there? No writes, no IO operations or nothing that essentially would make it block other operations. Pretty much. Yeah. Okay. Okay. So essentially, they are indivisible. They are just like the word atoms. Like they are the smallest, not smallest form of operations, but non-divisible operations. Pretty much. Okay. Let's see. Now, step by step project plan. So the first is the storage engine, obviously. So we need to create a simple file-based storage system with a fixed page size generally. Support basic operations like inserting, updating, and deleting rows. Add indexing, that's implementing a binary tree or a bit tree. Is that a binary tree? I'm not sure. I will check the specs for primary keys, and then support range queries and point lookups, and then the write ahead login. So after that comes the query processor, right? And this includes the parser, the planner, the executor, transaction manager, MVCC, locking and isolation levels, and then client communication, utilities, and tools, sub tools. Okay, now the tools that will be used generally, right? For parsing, the solution for norm and pest for SQL query parsing. Do I want to write my own SQL query parser? Oh no, obviously Tokyo for async. I'm gonna go with Tokyo because it's the more common one, and I know there's this thing going on with like people, like an argument in the ecosystem concerning whether we should all rely on Tokyo for asynchronity versus making the asynchronous ecosystem more open-ended, because now at this point everybody is supposed to do things the Tokyo way. But I mean, they pretty much solidified their hold on that part, and they're doing a good job generally. So, and I want reliability for the future, right, and compatibility too. So, yeah, Tokyo it is. Data structures, collections, and bean code for serialization. What's of SEDI? Why bean code? Let me just check. Take a look into bean code. Okay. So bean code it creates for. Interesting. When did the website change? Okay. So it creates for encoding and decoding using tiny. Hold on. I think I should also be able to share browsers since I'm not actively coding yet. Okay. I can duplicate you. Duplicate doesn't really give me the result I'm looking for. So let me do a window capture. Okay. Let's go for okay. Here we are. It's an interesting one. Okay. So here we are. Yes. So essentially, pin code is a crate for encoding and decoding using a tiny binary serialization strategy. Interesting. Using it, you can easily go from having an object in memory, quickly serializing it to bytes, and then deserializing it back just as fast. Okay. 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 So basic functions. I have a target variable, an option for string, right? And okay, bin code serialize it. Okay, and then unwrap the encoded, and then the code is the deserialization. Is this what I would need? It doesn't seem like a big deal. Okay. Let's see how much of can't say they do this. Is this important because of the binary thing going on? Probably. So with that said, let's dive in. Let's go with Okay, so let's get back on code. Let's see. Okay, let's see. We need to first of all. Okay, so we have bin code for that. Then obviously standard library file operations, right? And memmap for memory map files. Interesting stuff. Let's check that out. Memmap, memory mapping. Let's see that. Memmap. Is it memmap or memmap? Let's just Google it. Come on, come on. Do I have? Imagine I was on the wrong internet. Okay, let's run that back. Run it back. Okay, so memmap within Rust. There we are. It calls platform Rust API for memory mapped buffers. Somebody needs to explain that to me. Well, let's talk to our favorite Oracle, ChatGPT. Okay. Memory mapped buffers refers to regions of memory that are mapped directly to files or hardware devices, allowing efficient access and manipulation without the need for explicit read/write system calls. Okay. They are commonly used for high performance IO operations, shared memory, and direct memory access. Okay. So memory mapped files, file contents are mapped. Okay, memory mapped files. A file contents are mapped directly to a process address space. Yeah, and interesting. Allowing access as if it were an array in memory. Okay, so instead of explicitly writing to the file itself, in storage, the memory parts, the file access or the file contents are actually mapped to the process stack or heap, and they are being written directly, like as if it were an array. Arrays are truly the fundamental building blocks of the computer verse. Okay, now multiple processes can access the same memory map buffer for inter-process communication. Okay, that's how we can, and that way for doing IPC. But then they have to be properly monitored. Okay, hardware buffers used in low-level programming where a region of memory is mapped to a hardware device for direct access, like GPU buffers in graphics programming. I just read that. Let me just read it again. Used in low-level engineering where a region of memory is mapped to a hardware device, okay, for direct access, okay, like GPU buffers in graphics programming. Okay, yeah, I get that now. Fast file access, okay, avoid system calls like read writes, right, and also it is also going to be helpful because of OS specific syscalls that might have different underlying assembly implementations. Imagine that process of, like, trying to make all those individual calls one by one and having multiple different implementations. Well, obviously that's where the programming language comes to resolve the problem, but still that should be stressful for the process itself. But if I can just have it in memory, good stuff. Now we have a sample project structure. Okay, So we can have a source file and map our storage, map our queries, map our transactions, clients, utils, library, and then obviously main. I'm thinking of doing something interesting here. I'm thinking of breaking them down into multiple different crates, sub crates, and like, because I actually do like this sub crate pattern instead of just having the different folders as just individual modules in the project. I rather like have them as sub crates so that I can like git init in a sub crate and then make it a module or sub module and have it as a separate project entirely. That would be fun to do, and it depends on what the whole process is about. Now we have some learning resources. You see, I will not say, make no mistake, I'm not trying to be a database expert, but I tend to go deep most times, and I would love to go deep in this. Not because I find databases interesting, just because I really want to really know the language. So with that said, yeah, we're gonna read. So the first is around database system concepts, and that's for database theory in general. The second is designing database intensive applications. And the third is open source database, that is Postgres and SQLite. And there's a Rust database, an embedded database in Rust. I think that will be the first for me to really check out. Okay, that will be the first for me to check out. What do you look like? So we have the project here called SLED. Okay, a champagne of embedded databases. Okay, interesting. Let's see. Generally good structure. Okay, SNED is all down here for. Don't make me scared. An embedded database, right? So tree insert and get similar to STD B2 map. Yeah. Okay, range queries. Okay, tree query results in tree range. So. That is range queries, more like range select, and then this is for like insert and get, like insert key value pair. Then we have deletion. Then we have an atomic compare and swap, just compare values and swap them. Okay, and block until all operations are stable on disk, like a flush call. Doesn't seem to be much, but it's no progress. I mean, it's not SQLite or Postgres, but it's a database nonetheless, right? So let's see. Let's look at the scripts. I mean the 5 years ago. Commits from 5 years ago. Sheesh. Okay, we have a good amount of files in here. The tree. That just caught my attention. Let me just take a look at the tree. Okay, we have standard borrow cow. Okay, and then debug and self for formats. Then in num we have non-zero use 64. Okay, and then we have ops, like operations for range bounds and dereferencing, and atomic for ordering and sequential. Is this sequential counts? So just I'll look into it. So obviously we have parking lots. Is this a he has a sub module or a package in the project called parking lots? Let's see. Not trying to dive into loopholes right from the beginning, but sheesh. Where's parking lots? Okay, I can't find parking lots. Let's go back to the main base. Let's see what the cargo file looks like. Dev dependencies. Okay, and normal dependencies. So parking lot is a dependency. Interesting. Let's just check within. I'm not trying to check within mem map, please. I'm trying to check all of docs. What does parking lot do? Okay. Provides implementations of mutex and read write lock and convar and once. Convar a conditional variable. Okay. Noted. Conditional variable. What does that mean? I'll figure it out later. Okay. So, which means essentially, I could find their mappings or their rewrites in Tokyo, right? Yeah, I could find their rewrites in Tokyo, but this is just a good idea of what to do or how to do it. So, I want to see the main tree implementation, please. Let's see. Create struct for view with a lifetime generic of G and node view. It's supposed to leave that long. Okay. Where's view? Okay, we're implementing a dereferencing, also using G2 and with the target type of node for the return. And then we're also implementing into iterator for the reference to a underscore lifetime. Is that like general lifetime? Let me just touch a bit on the fundamentals. So I can just chat GPT the thing. So let's see. No, not just the underscore, please. I mean this underscore. Yeah. Meaning, please. Come on. Okay, you know what? Fuck it. I will skip it. Yeah, this underscore. Okay. Underscore. Let me see. Underscore lifetime generic in Rust. Yes, thank you. Or anonymous lifetime is used to indicate that the compiler should infer the lifetime instead of explicitly specifying one. Okay, noted. I was thinking it was static lifetime, but there's also static lifetime, right? Yeah, there's static lifetime on its own. Okay, let's get back there. Let's get back in there. Okay, so yeah, we have an out of bounds function. Okay, let's see the main tree implementation. Okay, a flash sympathetic persistent lock free b plus tree. A tree representing a single logical key space namespace buckets. Separate trees may be opened to separate concerns using db open tree. db implements the reference. I'm just assuming that is the reference, but let me actually go do this. Pick this copy. You see, in this case, instead of going to read the book, which is what I'm supposed to actually check out the book, right? I'm pretty much already touching on the three parts of this system, because for the most other parts I have some understanding, but they feel like they'll be much easier to understand. It's just that I want to know what the tree is used for. It's calling out to me right now. Like I really want to figure out what this. Sorry. yeah, I really want to figure out what this tree is used for, right? So okay. hmm So traits for that define operator overloading and general operations. Okay. Allows an object to behave like a reference by implementing automatic dereferencing, right? It is primarily used in smart pointers like box and RC reference counter. Okay, so something in me says that I understand this in English. Another part says, "Are we sure?" Normally, I come from a C++ background, by the way. But it wasn't for very long. It was during my very early days, and I only used it for about a year, and I switched to other languages like PHP. Yeah, I know. I'm sorry, but I know. I mean, it's not a bad language at all. It has actually really improved since then. But yeah, and I think I still remember more. I mean, coming back to Rust and Golang, I start to remember more about what pointers and um, passing things by reference and value and all the rest of them. The referencing are all about. Okay, so this is essentially okay. So automatic dereferencing operator. Hmm. Explain this in English. Explain in English, please. No, I understand the part about the reference, but then the way it's being stated here, the reference trait used, okay, allows an object to behave like a reference, right? By implementing automatic dereferencing operator. That is that part. Is that part that is confusing me? By implementing automatic dereferencing operator. Explain this in English. Mm-hmm. 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 Okay. Let us just refresh on the pointer arithmetics again. I think I have a note around that. I got the part of the reference, just that sometimes it confuses me every damn time. Every damn time. Just give me a second. Okay. Okay. So let's look. Let's dereference this. Okay. I mean, let's explore this. So int a. Okay. Asterisk p is a pointer to a. Yeah. The referencing p should actually give us 4. Okay. Yeah, because it's pointing, it's telling us, okay, tell us about the value. Okay, that's what the referencing is. What's that, please? Always keep this in mind. Okay, that is understood. Let's get back to business. Let's see. So that's what the ref does. It allows us to just access things with direct asterisk calls to be able to access the value that they represent, right? So all those asterisk is like the referencing of a pointer. That is crazy. C++ programmers. Damn. Okay. So now let's see. Into the sorry, hold on. Into the reference of the anonymous lifetime of the tree. Okay, like a reference to the tree. Why are we doing that? Why are we doing that? Why are we implementing for a reference to tree instead of the tree itself? Well, we'll figure it out later still. Now, the result here is a tuple of IVEC on IVEC. IVEC is what again? Is this type declared anywhere before now? Nope. Okay. Let's just go down to the tree. A public struct tree is a tuple struct, and and within it is an atomic reference counter for the tree inner struct. Okay, the tree inner struct is taking an IVEC. What is this? IVEC. Yeah, let's look at the implementation for that. IVEC. Okay, a tuple struct again that takes an array of size SZ. SZ is a constant of U size, it being the size of U size. Lost. What is U size again? Come on, quick answers. Unsigned size is used for indexing meaning. Oh yeah, it is OS based size for the bytes. Okay. And yeah, OS based sizing for the bytes on 64-bit systems is obviously 8 bytes. On 32-bit it is 4 bytes. Yeah, okay, noted. See, refreshing. Let's see. And this is size of size of call to use size. Yeah, this expression, what is the result of this generally? Is it just the actual byte size, or is it is a function from that returns the size of the type t in bytes? Okay, so it's the byte size, so it's 8 bytes now, right? It prints 4 on 8. Okay. That's interesting. Oh yeah, the page. So the page size 8 bytes, right? Okay, and that is the IVEC. It's an array of 8 bytes by 8. So 8 by 8, that's 8 by 8 bytes. That is almost like a square. Interesting. Almost like a square of 64 bits. Okay, interesting. Let's see how it's being used. Okay, so two tuples of 64 bits, that is 2 items in a tuple of 64 bits square. So 64 bits index 0, 64 bits index 1 are the results to item, and for which we are implementing an into iterator. So almost like iterating through. Okay, this is type item, right? Is type item a return type ever used here? Nope, it's not used in the trait implementation. Okay, but In the case for the inner tree, we have it as a tree ID, the IVEC, right? Are we using that as individual file bytes? No, it seems too small for the individual files themselves. That would be way too many files. Don't presume, Mozart, just continue. So we have the context, we have subscribers, we have atomic, we have root, which is an atomic U64. Tell me more about this, please. This is implemented in some sort of shim. The value here is a read write lock on a U64 variable, or rather U64 type. Okay, for now let's not dive any deeper than that. Let's just keep that at best. And the inner tree has a drop. We have a dereference for the tree, which is obviously just dereferencing the we're just dereferencing the 0, since the tree itself for tree target return is an inner tree, dereferencing 0, so the tree might actually be 2. As you can see, the inner tree is obviously atomic reference counter, so dereferencing the atomic reference counter in the trace implementation. Okay, and to insert into the tree, right, we take in the key value pair, right, where k implements an as reference, and the value can be converted into an IVEC. Okay, so the value essentially is being converted to the IVEC, and the guard is being pinned. We have a guard from pin with pin, straight up pin. Who has a pin? Is this from parking lots? I don't know. You know what, let's have some fun with this. This is really, really looking interesting. I like it. So I think it will lend a good hand to the project generally. So I'm gonna go ahead and clone a repository. How much time do I still have? Under an hour. Okay, let's do that. Let's get ourselves a repository, shall we? Hey, what's up? How are you now? Well done. How you doing? Okay, let's get ourselves a repo. Okay, browser capture out. Let's do this. Okay. Okay. Let's see. As it seems, not a big one, but an interesting one. Okay. So we can continue exploring this in here, but I don't want to jump the gun. I'm actually enjoying analyzing trees. This is going to be a long series, so obviously I would continue this process. I might do some look into B trees later on, but for this particular process right here, I have to get back on the horse, and I think we're going to take a look at the book on database fundamentals, right, so that I can get a very clear understanding of how I'll best use the architecture provided within SLED. I don't intend to copy any code. I just intend to learn and have my own implementations. Okay. This a buffer that may be inclined or remotely protected by an arc. The inner buffer is guaranteed to be. What's this macro doing? Do I want to expand it? Nah, I'll expand it later. I'd like to expand it, but I'd rather expand it into a different project. That said, let's get back on the docs. So let's see, database building. Okay, so next on my list is obviously taking a look at the books, right? So database system concepts. I think I can find this. Yes, okay. I think that's what I would need to work with. Okay. 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 Ta-da! So the idea here is not to read the entire book. We have about 1,376 pages. Nah. The idea here is to get the nitty gritty, the source, right? So I'll just go ahead and download this. I'll just go ahead and download this, and yeah, let's see, relational database. Okay, yeah, general relational structures. I think I understand this generally. Okay, let us actually go deeper, please. I might touch a bit more on the foreign key and the foreign key indexes, and yeah, foreign key and indexes primarily, and then the joins, yeah, and the implementation. Okay, and yeah, this is gonna be fun. This is gonna be fun. In that case, let me actually do this. Let me copy the link and add it to my Discord. Tools, resources, blah blah blah. Okay. Books. Let's have this here. Okay. Hold on. I think I'm gonna pause my stream a bit. Okay, I think I would have to stop here for now, although I'll still continue in my free time, but we are gonna have another one next week around this. Let's see if we can resolve. Well, not next week, maybe tomorrow or next tomorrow, I'm not sure, but let's see how soon we can get back on this grind. We have the SLED projects, yeah, right, and I'm gonna be going over it. Take some time to go over it. I really like the structure generally, and the use of terms like the IVEC, which essentially here is a buffer of 8-byte boundaries. Essentially, it is taking up certain space in RAM of about 8 bytes deep. It depends though on the OS type, 62 bits or 32 bits. So it will be 8 bytes deep or 4 bytes deep. right? And clone is implemented for it in order to clone it essentially, which will be pretty much fetching and rearranging it in memory again. Yeah. So yeah, that's about it.